After either our steel starts to yield or our concrete goes to the inelastic region, we're going to experience, or we're going to see inelastic behavior of our section. So it's at this point that our curve's going to start curving off, and at some point we'll reach our nominal capacity, our ultimate capacity, which in this class we'll call m sub n. So what will happen is our section is going to continue to rotate, and we'll have our neutral axis, and once again we can relate our strain to our curvature, assuming that our plane section remains plane. And we can assume that only the concrete in compression is going to contribute to our strength, so this will be our neutral axis, and we'll call the distance from the top down to the centroid here distance c. So then we can say that the distance down to the steel would be c, or would be d minus c. So whereas before, and we'll say that our maximum compressive strain is 0.003. So whereas before we could go from our stress or our strain to our stress diagram just using a linear relationship, now we're going to, I guess, to get the more precise behavior, we'll need to use actual stress-strain relationships for our concrete. So what we can do is, if we plot this, we'll get kind of our curve with a height of c, and the maximum height here being f prime c. Then we'll have some stress in our steel, which we can turn into we'll assume yield, but we can figure this out exactly later. So that this will create a tension force T. And then if we look at the centroid of this block, we'll get a compressive force C. So using these, the C value, or this compressive force and tension force, we have two forces. We would have a lever arm between them, and we could figure out our moment. So this is a little difficult to do. So what we'll do rather is we will approximate the shape of this section here using what's called a rectangular stress block. So the rectangular stress block, or the Whitney stress block, will have some height and some magnitude with assuming an equivalent area. So what we're looking for is this area to be equivalent to this area, and we want to try to have the centroid of this area to be equal to the centroid of this block. So what we'll find is, if we use a height of 0.85 f prime c and a depth of a, where our a equals beta 1 times c, we'll have about equivalent areas and about equivalent centroids. So then we'll still have our tension force T and our compressive force C, which we can put at the centroid of this block. So then our C will be equal to T, and our C is just equal to 0.85 f prime c times the width of our section times our beta 1c. So times beta 1c times the width of our section. And our tension then is just equal to the stress in our steel, which we're assuming is yield, times the area of our steel. So then we can solve for the depth of our compressive block. So we'll have our C equal to Fy AS over 0.85 F prime C beta 1 B. And then we can also solve for our moment. our moment just equaling a force, which we'll say we'll calculate our moment about C. So we'll just have our force AS Fy times our lever arm, which is D minus beta 1C over 2. So these are two expressions that we'll be using a lot in this course.